Hey guys, so we're going to be doing video homework number 3. So getting started, the first problem considers the vector field f equals x vector I plus y vector j, and tells us a little bit about the vector field and the lines that we're working with. The first part of this problem has to compute the line integral over C1, and C1 is going to be our straight line that we have here. So it's going to be, it says it right there. But the first step is to parameterize C1 from 1 to 2, from 1, 0 to 0, 2. So its starting point to its end point. So to first start off with this, we're going to put the bounds of t. So we're going to rewrite the vector or r, f, everything in terms of t so that we don't have x and y in the equation. So in this case, for C1, our t is from 0 to 2. Then we're going to write the equation of the line. We see that the slope is -2 and the intercept is at 2. So we write that out right here. And we're going to put y is equal to t so that we can, like I said before, put it in terms of something other than x and y. So I have that whole process right here, and we just solve for t. Then what we can do is we can make our r vector. So we have rt equals -1/2 t plus 1I plus tj. And that's coming from the fact that, again, our slope and our y is equal to t. So that's why we put t in front of the j component, because t goes with y. We go ahead and take the first derivative of r. That's the second step in computing a line integral. The first part is finding r, computing r prime, doing f of rt, and then dot producting frt and r prime t. So we take the derivative of rt and we get that value there. And then we're going to go ahead with the third step and plug in rt into f, which is what I'm doing right here. And you just, it's pretty simple, but you plug in your values for rt into your f vector, which we're given. That's that right here. We do that, we get this. Then we can dot product that with r prime t and put that over our integral. We already set our bounds of t, so it's going to be from 0 to 2. And we get this integral. So I went ahead and integrated that, and I got 3 over 2. The second step is to find the line integral over c2. So c2 is going to be our curved line. That's gonna have, instead of just a x component, or our x being to the first power, it'll be to the second power because it's parabolic. So this is the first method. We're gonna use use a parabolic curve as opposed to an ellipse, using cosine and sine. So very similar process. We find our equation of the line, which is our y right here. We're gonna do x is equal to t for this one. Plug in t for our x, and then we're going to get our rt value, which is just adding our x and y components. So our x is equal to t and our y is equal to -2 squared plus 2. So we plug that in for rt. I did also set the balance from 0 to 1 for t. Take the derivative, do f of rt, kind of getting repetitive, but very similar process. These are just the steps that you have to use to parameterize and calculate the line integral. Then we go and dot product our f of this should be f of rt dot dr, and our dr is our r prime t. So same thing that I wrote before, but just different symbols for that. I dot product those aside from this just because, again, I didn't want it to get repetitive. But we get a negative integral from 0 to 1, t plus 8t cubed minus 8t dt. Go ahead and integrate that, and we get 3 over 2, which is good. We want to get the same values for all of these. I'll get to that in a little bit. So then we see method 2, it's saying as an ellipse, so we're going to parameterize it again and then compute the integral of c2 f dot dr of direct integration. So when you're doing this as an elliptical, you have to put x and y in terms of cosine and sine. So our x is cosine, our y is sine. And the bounds here, because we're working with like, thinking of it as more like a circular shape instead of it just being like 0 and 1 or 0 and 2, it's going to be 0 to pi over 2 because we go from, I'll show it up here, but we go from the beginning of the unit circle, which is 0, and this is the first quarter or the end of the first quadrant of the unit circle, which is pi over 2. So we set that parameter. Again, same process. I feel so repetitive saying it, but our x component for our t is going to be cosine t, and we have to add that vector I, and then our y component is going to be 2 sine t, and we add the vector j. Go ahead and derive that, plug rt into f, and we get the same thing for f of rt that we do for rt, and then dot product f of rt with r prime t, and this is what we get right here. Integrate that from 0 to pi over 2, and we get 3 over 2 again. Again, great news, we want the same answer for all of these. We're going to go ahead and use the fundamental theorem for line integrals, or the fundamental theorem of calculus, to like explain why it's path independent and explain why we're getting the same answer for all of these. So I have the fundamental theorem of calculus again right here. It's the integral of c grad f dot dr equals fq minus fp, where fq is our final point and fp is our initial point. To help us do this, we're going to start with the curl test. The curl test helps us prove if our vector f is path independent or not. So we have our, I kind of like shorthanded it, but we have here our vector f. The first part is going to be your f1, the second part is going to be your f2, so your I component is your f1, and your j component is the f2. So I derived, our f2 is y, so derivative of y over x equals 0, and f1 is x, so we're going to do derivative of x over y, which is also 0. So we see here that if the derivative of f2 over dx minus the derivative of f1 over dy equals 0, then that's good. It helps us with our curl test. We also do not have any holes in our function. Our f vector is xi plus yj. There aren't going to be any holes. It's continuous. There's no like denominator or anything that would make this like have a point where it's not equal to anything. So you see here no holes, and the partial derivatives of those two things are equal to 0. So then we see that f is path independent, which is great. So we can go ahead and, well, path independency and also this kind of shows that it's conservative. So that answers the first bullet point, kind of. Then we're going to find the potential function. So to find the potential function, you're going to take the derivative of f with respect to y and the derivative of f with respect to x. So our f is just xi plus yj. So we're going to get y and x, and then you go ahead and integrate that. I kind of skipped a step here, so I rewrote it, but you basically separate the integrals with respect to each of y and x, and then add them together. So we finally get this, don't forget the plus c. And then to finally compute the fundamental theorem of calculus to further prove that we are on a continuous path, we're going to plug in our initial point, which is 1, 0, and our final point, which is 0, 2. So we're going to do the final, which is right here, minus the initial. So we get 2 for the final and 1/2 for the initial. You do 2 minus 1/2, and look, we get 3/2 again. So by getting the same value for all of these, we see and show that it is path independent. Okay, and we also know that it is conservative because the line integrals that we did for C1 and both methods of C2 are all equal. They're all 3 over 2. So they're equal. It means that whatever path we take from point 1 to point 2 doesn't matter. We're always going to get the same answer with this line integral. So we are basically proving that it is conservative and path independent, and therefore any of these methods work and can be applicable to find the solution, or what the line integral is for this function. Going on to problem 2, we have this is a little different. It is a closed surface, and we have 3 different lines. So I noted them as C1, C2, and C3 going in counterclockwise direction. We have the same vector field xi plus yj. the first step is to compute the line integral over each segment. So went ahead and did that. Again, same process as before. I'll run through it quickly. So our C1 is from 0 to 1. Our T is going to be from 0 to 1 in this case. That T-bound can be set by whatever you want it to be as. So it just kind of depends on how you like put your slope and what you make as your T. Like if you set y or x equal to T. But our C1, as we can see, is only moving, that's not gonna work, in the x direction. So we only have one component to worry about, which is our x component. And it's increasing slope of 1, so our value is just ti. The derivative of that is the I vector. Plug rt into f, we get t vector I, and then dot product of those, and we get t vector I. So we can go ahead and integrate that, and we get 1/2. For our C2, it's going to be a little different because we have both x and y components, and this is the same line that we did in the first problem. So I'm not going to go through this math again and talk it out, but we get a value of 3/2. Our t is from 0 to 2. And again, wrote the slope of the line. We set our y equal to t. The y is equal to t or y is equal to x. Again, just depends on what slope you're finding and how you want your bounds of t to be. So I just picked 0 to 2 because it's easier in this case, and that y is equal to t again, just because it's easier to solve for this line. Go ahead and get all that, we get 3/2. Now for our C3, go back up here. It is just a line in the y direction. So it's a straight line. We're going to have no x component. It's going to be very similar to part C1. So we have a slope of -2t, and our starting point is at 2. So it's kind of like, think of it as like intercept. So we have -2tj plus 2j. Take the derivative of that, plug rt into f, and then dot product f of rt and r prime t, and our value for that is going to be -2. I'm going to go back over like how you get each of these lines. So C2, it has an intercept at 2, so that's why we like the +2 obviously right here, and we set our y equal to t, so that's going to be our j component, and our x obviously is going to be our I component. Again, I feel so terrible saying this, but I feel very repetitive going over these steps over and over again because we did this calculation just before. The next part of this is going to sum the line integrals. We know that we can do that from this little theorem right here. We're going to add C1, C2, and C3, so I wrote our values, 1/2, 3/2, and -2. And so these equal to, it's just going to be 2 minus 2, which is equal to 0, which is great. This helps to prove what we're going to be proving in part 3. So once again, we're going to be using the fundamental theorem of line integrals, or the fundamental theorem of calculus, to show that f is a conservative vector field. We have no holes, again relating back to the curl test, and I'll show you right here that the curl test equals 0, so we know that it's path independent. We took the derivative of f2 over x and the partial derivative of f1 over partial derivative of y. They're both equal to 0 because we start and end at 0, 0. They're both equal to 0 because the derivative of y with respect to x is 0, and the derivative of x with respect to y is also 0. Then we're going to go ahead and find the potential function as we did in the first problem. So partial derivative of f with respect to x is going to be y. Partial derivative of f with respect to y is going to be x. Go ahead and integrate those. I didn't writing them out separately because I did previously. We get y squared over 2 plus x squared over 2 plus c. Once again, our starting and final point is 0, 0. So we're going to have our f of q is going to be f of 0, 0, and our f of p is going to be f of 0, 0. And when you plug both of those in, you get 0 because you're going to have 0 in the numerators across all points because those are the only places that your x and y are, and you're not adding or anything in the numerator. So we get 0. I'm going to go ahead and explain this a little more, but when the result of a line integral over a closed path is 0. It shows that, like, again, going back, relating to problem 1, the path taken doesn't matter, and the sum of all of those is always going to be equal to 0.